Welcome to Transfer Phenomena in Bioprocess Engineering NPTEL course. So, last class we discussed about the fluid flow dynamics in the flat plate, but today we will discuss about the circular tube, how this one. So, why you want this one, especially this the fluid flow through circular tube, the very fundamental transfer phenomena like bioreactors, heat exchangers, then fermenters, membrane, chromatic column, all is very important for this one. Sometimes the bioprocess system like cell suspension, culture media, enzyme solutions, the buffer, everywhere we will use a circular tube. We need more understanding how the velocity happening, velocity is whether this will become critical or not, everything we need. So, the shear stress distribution also influencing cell viability and morphology here. So, again the residence time also affecting the bioreaction kinetics here. So, the mass and heat transfer rates very crucial for the substrate delivery and then product removal. So, the flow of liquid through circular tube is definitely under the influence of pressure difference and gravity, the both will be there. The vertical tube has length L, the length is L, the radius is R. The assumption is the velocity is constant, V we keep as a constant, okay, then the density and then viscosity both is a constant. The density of this one, viscosity both are constant. The flow is the laminar, but we can use even turbulent also, but for simple condition we always assume is a laminar. So, definitely the Reynolds number should be a less than 2100, less than 2100. So, steady state condition. So, there is a two different steady state, unsteady state. If it is time dependent, then we always called as a unsteady state. If time is, we want to calculate, if time is 0 or is a time independent, then we called as a steady state. Wherever steady state, the time always independent. So, we always assume steady state condition. We can solve unsteady state also, but it is very difficult to solve. There is a accumulation term will come. So, it normally is very difficult to solve. So, the Newton's of viscosity is applicable, the tau equal to minus of mu dV by dr. The previous one we discussed about the Newton's law, tau equal to minus of mu dV by dx, but here we are talking about a circular tube. So, this is a radial direction. So, this dr also will change. You take the here, this is a pipe of this one, okay, simple for understanding, okay. I am also writing here, or I will write here to understand, very easy to understand. So, here this is a x direction, okay, z direction, the another one is a r, the radial is r. So, this is the direction, the radial is r, and whenever the flow is there, that is z direction. So, here three things important. One is for velocity, how looks velocity here, how looks the shear stress here. So, that this place at z equal to 0, this point is at z equal to 0, the point is here z equal to 0, then z equal to L. Because the circular tube, there is z equal to 0 to L. Same way for is the radial direction, then axial direction, okay. And this is the axial direction, then what will happening this one, the radial direction also, the radial direction also what is happening. So, here at this point at wall, the pi value, the pi of x z, what is happening. Same way for this point at center point, what is the pi value, okay. So, the pi value is the center point here and this one, but the thickness we will write for delta r, but the previous one the thickness we always write as a delta x, but here we are writing the thickness is the delta r. And Newton's law of viscosity, of course you know Newton's law of viscosity, tau r is equal to minus of mu dV z by dr, we discussed this one. The previous one for flat plate it is a dx, but here is a dV z by dr. Of course, this another one is the pressure effect. So P is a function of z, is the direction. So now we want to solve this one. The first is for convective across the annular surface. Then there is a cylindrical surface also there. Then due to gravity here. So here the 2 pi r delta r, it's the area of that one, 2 pi r delta r, then pi z here. So if we solve it, then we will get a rate of momentum. What is at z equal to 0 or z equal to L. So here we are solving two ways. What is z equal to 0 and z equal to L, how the rate of momentum will be here. Then the gravity force, of course we have to add here the gravity force, there is a 2 pi r delta r L, this is like meter cube, then the rho g is there, the density, then gravity. So first one is annular surface, then what is the across the cylindrical surface, the cylindrical surface here, what is happening here. So at r or r plus delta r, so there is the unit, this one, the 2 pi r L, again pi of z by z, the pi is a function of shear stress, then velocity, both convective and stress here. Same way here also, the 2 pi r plus delta r. So the movement transport by convective and molecular here, the pi z, pi r z here, the first one is we are writing in terms of the cylindrical, then annular surface, then due to gravity. But the accumulation here 0. If because we assume as a steady state, so then this guy is coming 0. If you assume as an unsteady state, then we have to bring a variable here. So because when you use here unsteady state, then the accumulation term also will come like differentiation dou c or whatever, okay. So it's very difficult to solve. But if you want to solve it, you make life easy, you always assume a steady state and make it 0, then it's easy to solve. Or otherwise we have to use a MATLAB. If you use like unsteady state, then the dou c by will come, then we have to use for ODE 45 solver. We used to teach in the class, so ODE solver. So then from there we can derive the, we can get the what is the concentration or what is the shear stress, this is all we can, velocity, everything we can get it here. So now you have to take in terms of limit, because the previous problem we used to delta x tends to 0, but here all in terms of radius, so delta r equal to 0. So you take a limit, then we will get a beautiful expression of this one, then there is a rho g of this there, okay. You divide by throughout the problem 2 pi r L delta r, so that we will get everything cancel here, so the delta r will come here, here always the 2 pi r will go, then finally we will get a rho g. Yeah, divided by 2 pi r, same here, 2 pi delta r L. So now we got this one pi of z here, you differentiate this one. So then we'll, before that one, the pi of here, the pi is the pi of r z equal to tau r z plus rho of v r and v z, both will come here. So one is for Newton's first law, we can use directly Newton's first law. Other one is for convective this one, okay. So other one is for like viscous effects, because Newton's law, wherever viscosity is there, there is a viscous effect. Then this is a convection, this one. So now pi z is equal to p of this one, tau z rho v z by this here. Then after simplification, then we will get the beautiful expression of p minus 2 mu of this one. So what the assumption here, the v z equal to r and v r equal to 0, then the p is a function of z, the pressure is a function of z, not x. Because the previous problem we discussed x, but here is a z and r, only both side is a variable with respect to varying this one, so we have to use for z here. Same way for equation 2, you take that one and after modification we get the mu of this one. Again equation 3 also same way, we get a p of minus 2 mu dvz by dr. So of course we know vz equal to vz of r. After substituting, then we will get a simplified form. d of r by r tau r z equal to, this equation will come. Then finally we get this one is P equal to pressure, P equal to P minus of rho g z. We always write the pressure, we can write in terms of rho g h here, the pressure head we can write like this. So tau r is equal to P naught, what is that, z equal to 0, what is the pressure, and z equal to L, then PL by 2L, then C1 by this one. So after integration, so now we have to apply at r equal to 0, that tau r is equal to infinite value. So here tau r is at infinite value, then automatically r equal to 0, then C1 should be also 0. So substitute G1 equal to 0, then we will get tau r is equal to P naught by PL, P naught minus of PL by 2L into R. So tau r is equal to, because if you substitute this boundary condition, there is a two is there, one is a boundary condition, other one is for initial condition. Whenever initial condition you want to use, when time t equal to 0, we call as the initial condition. But boundary condition with respect to boundaries, right? You have to write z equal to 0, what is the value, or z equal to L. There is a boundary condition, two type of boundary conditions there. The mixed boundary condition, the normal boundary condition is there. These are all very normal, this one, this is like complex boundary condition. If you use complex boundary condition, it's very difficult to solve. So then we have to apply the Newton's of viscosity of equation here. Of course, this tau equal to, we substitute tau equal to minus of mu dvz by dr. Substitute, now you integrate this guy. So integrate this one, there is a after integration we will get for Vz equal to P naught plus P1 by r square 2. So now we have to apply boundary condition at r equal to r, what is the value of Vz? At r equal to r, see these are, you assume here r equal to 0, the velocity is a high maximum here, and wherever the solid surface at r equal to r, then velocity Vz 0, it's become negligible, because there is no velocity, this completely shear stress is the maximum this point. So you substitute here r equal to r, then V set 0, this point is 0, then this convert as a r square. So C2 we got, now we know what is the value of C1 and the C2, you substitute this one, then we will get a beautiful expression of this point. So the V z equal to velocity equal to P naught minus PL by 4 mu L r square 1 minus of r by r square. So this is like incompressible flows, Newton fluid, the circular tube is parabolic. Okay. You just see here, this is a very simple, and this is our radial direction, and here is the z direction. Okay. So velocity profile, just see, is very beautifully the parabolic velocity profile. Vz is a function of Vz equal to Vz function of r. So this point, wherever this point, okay, the Vz 0, but this point is Vz equal to V max velocity, and this point maximum velocity, but this point is V0. So wherever Vz V0, that the shear stress is the maximum, the shear stress is the maximum. Wherever V0, the shear stress is the maximum here. Wherever V equal to V max, then the shear stress tau equal to 0. So this point, that's only they are mentioning, like shear stress is 0, but velocity is the maximum. For this point and same way this point, both side, the velocity is 0, then automatically the shear stress is the maximum point. So that's only they are giving here. So the V max, what we can do, V max here, the P naught by P L 4 mu L by r square, because V max where we will get, when r equal to 0. If r equal to 0, this is all okay, we will get only up to this expression. That's only we are giving V max, maximum velocity, the derivation from this equation. So once we done, that's we know V is equal to V max 1 minus r by r square. Now we have to go for average velocity. Average velocity we can do only for r, Vz, dr and d theta, because throughout the pipe we have to use 0 to 2 pi, then 0 to r. So we already solved this one. Then now we have to see, it should look like velocity, V is at average velocity. So, same is 0 to 2 by 0 to r or d theta. So, we will get a velocity. What is the average velocity here? You substitute everything, then we will get a Vz equal to P naught minus PL. This is the equation, P naught minus PL by 8 mu L r square. So, the P naught minus PL is the pressure difference here, then mu is the viscosity, L is the length of that one. So, after solving this one, we can get average velocity Vz equal to V max by 2, maximum velocity by 2. So, we will get the maximum velocity divided by 2, we will get the average velocity of here. So, once this done, then we have to calculate a Q, volumetric flow rate. Volumetric flow rate, how you have to calculate? V, I am repeating once again, area, because V is the velocity, that is a meter per second, then area is a meter square. So, multiply this one, then we will get a meter cube per second, that is a volumetric flow rate. There is a derivation of volumetric flow rate over the cross section of completed one. Anyway, then you have to integrate 0 to r. After integration, rearrange, then Q we get, we got Q equal to pi of V max by r square by 2. That is called Q is a volumetric flow rate here. So, then volumetric flow rate, then what is the mass flow rate? Mass flow rate, we always use mass flow rate equal to that M or W, whatever you can write here. So, then here Q into rho, because this is a volumetric flow rate meter cube per second, then density kg per meter cube, volumetric meter cube per second. Okay, so I think so this unit is kg per second, mass flow rate is a kg per second, we will get from here. So, pi P naught minus PL rho of this one. So, this is called as the Hagen-Poiseuille equation. It will be used for laminar flow, only for laminar flow we always use the Hagen-Poiseuille equation. So, this is a very standard equation, the pi of P naught minus PL rho r for 8 mu L. Only we can use for laminar flow this equation. So, we just for what is a Hagen-Poiseuille equation here, we always use for only for laminar flow, and it should be a only valid for fully developed flow. So, even this equation can also be used for the viscosity in capital T for flow viscometer. We will discuss more on the forthcoming classes, what is the laminar flow, what is dermal flow, then some what is the real situation, how the reference pipe can create as one. The summary of assumption here, what we made here, the flow is laminar, but the Reynolds number definitely should be less than 2100. The density is constant only for incompressible flows, but the gas phase we cannot say the density constant, definitely vary. So, only incompressible liquid phase. The flow is steady because that does not change with the time. So, the T here, if is steady, then T always 0, that is the independent of time. And we also assume the fluid is Newtonian fluids, then only we can solve it. If non-Newtonian, that there is a n, power n will change that one, it will make complicate here. So, the end effects also are neglected for this one. The summary of the assumptions for here, we always go for this one. We assume as like a laminar flow. We just started to discuss first flat plate, what is that one, then the circular plate, what happened that one. So, once we started to derive, there is a boundary condition, the C1 and the C2, then we have to use two boundary condition, because if there is a two constant, see example here V is equal to C1 plus C2 is coming, two constant is there, we cannot solve just like that. When you want to two constant, you need two boundary condition to bring here, then only we can solve it, otherwise we cannot solve. That is only we always use the two boundary condition to solve that one. At x equal to 0, what is the value of dV z by this one, then x equal to r or delta, what is the Vz value. So, like that we will discuss more on this one. This is a small problem, you just okay for to understand here, the internal diameter is there 3.5 10 power minus 3 meter, the length is 0.45 meter capillary. Then the flow rate of density is 875 kg per meter cube. The density of the flowing fluid is 875 kg. So there is a viscosity is there, viscosity 1.3 10 power 3 Pascal second viscosity here. The pressure drop, the delta P pressure drop equal to 0.075 meter. Then the density of water is rho equal to 996 kg per meter cube. So everywhere here 996 G value. Then the next one is for pressure drop across this one 0.075. So pressure drop we can make as a Newton per meter square. Many units are there, Newton per meter square. So then Pascal, many units is there, mmHg, millimeter mercury. So even so many units are there, the pressure drop. Then the viscosity here, the Pascal seconds, all values are given. So now what they are asking here to calculate the average velocity of the liquid. The average velocity of liquid U meter per second. Once U done, then we have to calculate the volumetric flow rate. Volumetric flow rate is a Q value, okay, because average velocity done V into area, so we will get a volumetric flow rate here. So next is the Reynolds number. Of course, Reynolds number we know, Reynolds number equal to dV rho by mu. From there we can calculate whether this is a laminar flow or turbulent flow or what type of flow. So verify whether the flow is the laminar or turbulent. For that purpose only we want to use here. So the pressure drop, of course, we always calculate the pressure drop equal to rho G H, the pressure, okay, drop here. So rho is the density of water, we know a value, then G is the 9.8, the H is here, already given value, okay, H is the, what is the height of that one, okay, 0.075 meter of water here. So from that delta P we found that one 738.2.8 Pascal. Once this done, of course, we know what is the Eigen-Poiseuille equation. So U equal to delta P by d square by 32 mu L. So we know value of delta P, then diameter of we know that one, then 32 mu is the viscosity, L is the length of that one. All problems the value is already there. The length of capillary, all L also 0.45 meter. You substitute all, then we will get here velocity. Velocity is a 0.480 meter per second. Its average velocity. So then area equal to pi d square 4. Area we know, area equal to pi d square by 4. So you know the d diameter of that one. Go back, you can get the value of the diameters here. Okay, diameter of pipe is here. So then we will get 1.25 in this one. After solving, we got area of the cross-sectional area of the capillary. So once we done velocity, then volumetric flow rate, then area also. Then what is the volumetric flow rate here? Volumetric flow rate here, that we have to calculate here. So Q equal to UA. The U we got from the previous one, the velocity. Okay, the area is the area of the problems here. The velocity here already there, meter per second. Then area meter square. So we will get in terms of meter cube per second. So now we know volumetric flow rate. Then we know the velocity U value. Then we know diameter of that. Okay, internal diameter of this one. So we know everything, and the mu viscosity also know. You substitute everything, then get the value of Reynolds number. So here Reynolds number is a 1131. It should be less than 2100. So its fall is the laminar flow, because we are only discussing, whether it's a laminar flow or turbulent flow on this one. So whenever fall less than Reynolds number this one, then this Reynolds number is 1131, is a laminar flow. So overall picture, what we already discussed many classes, the Reynolds number less than 2100 we called laminar flow for circular pipe. The 2100 to 4000 we called as a transitional region. If it is Reynolds number is a greater than 4000, we called as a turbulent flow. So Reynolds number we got 1131, it's a less than 2100, then the flow is a laminar. So what is the final solution of here? We got the value of average velocity, then volumetric flow rate, then Reynolds number. They asked whether it's a laminar flow or turbulent flow. All this one, it should be a laminar flow. So far we discussed that one. Then now we discuss the biological problem. It's like quite interesting this one, but same. It's very simple. It's not very this one. The blood flows through artery. having the radius is there r value, radius of value r equal to 2 into 10 power minus 3 meter radius. The length of this one, the length L equal to 0.1 meter. There is a volumetric fluid, the volumetric fluid Q equal to 2 into 10 power minus 6 meter cube per second. The volumetric fluid is there, the length of water is there, then radius also there. So, then what is the viscosity of blood? Viscosity of blood mu equal to 2 point here, this is the mu value 2.084 into 10 power minus 3 Pascal per second. So, what is the density of the blood? Density of blood is here 1060 into 10 power 3 kg per meter cube. So, all values are given, radius, then length, then volumetric flow rate, then dynamic viscosity, then density of fluid. All values we know, then we have to calculate now. But what they are asking here? They are asking first average velocity of blood flow. So, what is the average velocity? Because we know volumetric flow rate, then velocity we can calculate very easily. Then what is the pressure drop across the artery they are taking? So, then Reynolds number, whether it is a laminar flow or turbulent flow, if Reynolds number no, then what we can identify whether it is a nature of flow or the something different. Okay. First we have to go average velocity of this blood flow, average velocity, the velocity here V, the Q by A. So, V velocity we need Q by A, that is only. So, go to first area pi r square, we know area pi r square. You just put the value of pi r square, this value, then you substitute, then V equal to, because area we know, area this value, then Q is the volumetric flow rate here. Volumetric flow rate is already given the problem. What is the volumetric flow rate here? 2 into 10 power minus 6 meter cube per second. So, divided by area. So, Q by A, we get a velocity, because here meter cube per second, the volumetric flow rate, then this meter square, both will get cancelled, then finally we get a meter per second, that is the velocity units here. So, velocity once you got this one, next you got to calculate for the Reynolds number, okay, because velocity we found, then whether we have to see whether it is a Hagen-Poiseuille, using Hagen-Poiseuille equation, whether it is a laminar flow or not. So, this is a standard formula P Q equal to pi r power 4 delta P, this is a r by 8 of mu L. So, this is the radius of that one, the delta P is a pressure drop, then mu is the viscosity, then L is the density, L is the length, sorry. So, from there we can calculate delta P, the pressure drop here, So, here after rearranging all equation, use the viscosity value, then the length of this one, then volumetric fluid, what we got here, the same fluid, volumetric fluid here, already given the problem, 2 into 10 power minus 6 here, volumetric fluid. What's the volumetric fluid? Then we have pi r power 4, r is the radius of the artery pipe here, radius of artery pipe 2 into 10 power minus 3 meter. So, it's r power 4. So, after solving, then we got a pressure drop equal to 66.34 Pascal. Normally, the blood flow, it should be a laminar, because sometimes with turbulent, that is not, normally it is not possible, it should be laminar flow. Whenever the turbulent and Reynolds number is getting increased, there is a health issue here. So, the Reynolds number you know, Reynolds number equal to dV rho by mu, the rho density we know, density is the density of blood here. Then velocity we found, velocity from previous problem 0.1592, velocity here 0.1592 meter per second. So, then the 4 into 10 power 3 is the diameter of that one, d is d value. So, d also here, the radius here, so d equal to 2r, okay, because already radius is there, multiply the 2, so we will get a 4 into 10 power minus 3 meter, that is only where they are using a 4 into 10 power minus 3 meter. So, then mu viscosity problem already given 2.084, this is viscosity. So, you can use all and get the value of Reynolds number. See, Reynolds number is the less than 2100, then it should be a laminar flow, because this is a laminar flow is laminar flow. If it flow is laminar flow, Reynolds number should be less than 2100. If it's 2100 to 4000, we call it as a transitional here. It's all we are talking only circle pipe here. So, if Reynolds number is greater than 4000, then we call it as a turbulent flow. So, since the problem is we got only Reynolds number 324, the flow should be a laminar. Thank you.